Imagine you are trying to open a locked door. You have a key and you repeatedly try to turn it, but the lock simply will not budge. Now picture that same key but with a different kind of push. The lock clicks open instantly. What if light, our everyday understanding of energy, sometimes behaved in a similarly counterintuitive way, defying all expectations? Classical physics, primarily based on the wave theory of light, found itself in a perplexing situation when attempting to explain the photoelectric effect. It simply could not account for several critical experimental observations regarding how light ejects electrons from a metal surface. The core issue stemmed from classical physics predicting that the energy of emitted electrons should directly depend on the intensity or brightness of the light. According to wave theory, a more intense light wave would carry more energy, transferring it to the electrons and causing them to be ejected with greater kinetic energy. It also suggested that if light intensity was very low, there would be a measurable time delay before electrons accumulated enough energy to escape, similar to a small bucket slowly filling with water. However, experiments revealed a completely different story. First, electrons were only emitted if the light's frequency, or color, was above a specific threshold value, unique to each material. Below this threshold, no electrons were ejected, no matter how bright the light source or how long the light shone on the material. This was a profound contradiction to classical predictions. Second, if the light's frequency was above this threshold, electrons were emitted almost instantaneously, with virtually no time delay, even when the light source was incredibly dim. This rapid response defied the classical expectation of energy accumulation. Third, the kinetic energy of the emitted electrons depended solely on the light's frequency, not its intensity. A brighter light above the threshold merely ejected more electrons, but not faster or more energetic ones. These three observations were irreconcilable with the established wave model of light. The breakthrough came with Albert Einstein, building upon Max Planck's earlier work on quantized energy. Einstein proposed that light itself consists of discrete packets of energy, which he called photons. Each photon carries a specific amount of energy directly proportional to its frequency. When a photon strikes an electron, it behaves like a tiny particle collision, transferring its energy to the electron in an all-or-nothing exchange. If a single photon possesses energy greater than the material's work function, which is the minimum energy required to free an electron, that electron is immediately ejected. If the photon's energy is less than the work function, it cannot dislodge the electron, regardless of how many low-energy photons bombard the surface. This elegant quantum explanation perfectly matched the experimental results, solving the classical physics dilemma. This phenomenon firmly established the concept of wave-particle duality, meaning light exhibits both wave-like and particle-like properties, a truly mind-bending idea at the time and a cornerstone of quantum mechanics. It also cemented the idea of energy quantization, where energy exists in discrete bundles rather than as a continuous spectrum. This foundational understanding was not just theoretical. It paved the way for practical applications such as solar cells, light sensors, digital cameras, and photomultiplier tubes, which are vital in countless technologies today. The photoelectric effect was not just a scientific curiosity. It was a pivotal moment. It provided undeniable evidence that our classical understanding of the universe, while effective for everyday scales, simply breaks down at the atomic and subatomic levels. This profound realization propelled physics into the quantum age, forever changing our perception of energy, matter, and the fundamental laws that govern them.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.